thank you for the introduction. First of all, I would like to thank USACM for giving me the opportunity to talk this morning, and to all of you for tuning in for the talk on predictive models of skin through the integration of machine learning and computational mechanics. And before I dive a little bit into the details, I just want to give an overview of the type of research that we do in my lab. We basically work at two main thrusts of computational mechanics. On the one hand, we are interested with the recent advances in machine learning and the success that it has had in other fields, such as computer vision, for example, with the fact that we are getting more data than ever before and that our models are becoming more complex. One of the thrusts in my research group is this integration of mechanics and machine learning, which will be the topic of today. And then on the other hand, even though I won't cover it much today, we also work at developing theories and numerical methods for the integration between mechanics and mechanobiology. So not just understanding that tissues grow and remodel in response to the environment, but also how do they do that? What are the control mechanisms at the cell scale that drive this process? So we also do work in that direction, although that won't be the focus of this talk. And even though we work across several applications, the main application or the main model system that I have been using is skin as a model system. And this is because it's easily accessible for experiments, and also because there's many different applications that we can look into. So we do work on wound healing and pressure ulcers. We do work on skin growth, and we do work on reconstructive surgery within this application of skin. And today I'm just going to talk about the skin growth and the reconstructive surgery work, and primarily this integration of mechanics and machine learning. So let's get started with the reconstructive surgery. The motivation for this is that even though the molecular mechanisms are not completely clear, it is clear that stress leads to wound complications. And this is one example that I have from my collaborator, Dr. Arun Gosain at the Lurie Children's Hospital in Chicago, whom I work with closely. And just a disclaimer that there might be some pictures in the talk that are maybe a little bit graphic in nature. So, but yeah, I grayed out a few of them, but just beware. What you can see here in panel A is a case of an 11-year-old that has a giant lesion in the skin. This is a nevus that needs to be excised because of potential for malignancy. And the way this is done is expanders are placed underneath the skin and inflated gradually over a couple of months. So this process takes a while, but the skin gets stretched and it grows in response to this inflation. And then at the end of the day, in panel C, after a couple of months, you take out the expanders and you have extra skin that you can use to resurface the defect. The problem is that without any sort of predictive models, what happened in this case was that the sutures were closed under a significant amount of stress. And then this is a region that has a lot of movement. So the wound kept on opening. So that's what you see on panel D. It got infected. There had to be some tissue debridement. And then it was left to heal by secondary intention, which you see in panel G. And unfortunately, when you have these large wounds healing under secondary intention, which is basically just trying to prevent infection, is that they lead to pathological scarring and contracture. And that's obviously not a good outcome. So we would like to avoid that. And my collaborator, Arun Gosain, has a strong interest in doing that. But there are some challenges. So clearly, having predictive models will be useful, but there are some challenges. Some of the challenges are that there's uncertainty in the mechanics and the mechanobiology of these tissues and these responses. The fact that we would like to have some general recommendations, but also be able to specialize for patient-specific cases. The fact that we want robust models that are computationally efficient so that we can really apply them in the clinical setting. We want to be able to do optimization under uncertainty. And we also don't want to start from scratch. We want to use as much information as we can, either from previous clinical experience or human data, even if it's kind of sparse, but also animal and in vitro data. So computational mechanics is a tool that can be used to address some of these challenges. And I would say computational mechanics plus. And that plus is going to be some of the emphasis of this talk. So some of the ingredients that we need to do this preoperative planning, the first ingredient would be the geometry. So this is another case representative of the type of applications that we work on. This is a 7-year-old girl that had a lesion in the scalp that needed to be corrected. Again, there was a tissue expander placed and growth over a couple of months, so you had extra skin to correct the defect. And there are several options to get 3D images. We have used our own stereo vision system. We have a 3D camera system that we have used. But I would say my favorite one is multi-view stereo algorithm. And this is because it doesn't require specialized equipment. All you need is a standard digital camera. And as long as you take enough pictures from different angles, usually 30 to 50, you can reconstruct a pretty good geometry. And we have used this technique. In this case, we not only collect the information before the surgery, but also during the surgery and after the surgery, because we're interested in the whole pipeline. Although in the future, ideally, getting the information only before the surgery should be enough to set up the model and make some prediction and possibly some clinical recommendation. So what you see at the bottom is the type of geometry that we can get with this setting. In this case, we also had a CT scan, but that's not always available. So that's one of the ingredients. Then the other ingredient are the material properties, or the mechanical behavior of the tissue. And in the behavior of collagenous tissues, such as skin, has been characterized quite a bit. We use this among many other models. We use the strength energy proposed by Holzapfel, Gasser, and Ogden, which I'll refer to as HGO. It's a hyperelastic material, and it has this characteristic exponential response of the tissue at larger stretches. And this is something that is acknowledged for other tissues, not just skin, but definitely for skin. And then in particular, I use the strength energy function because there are some experimental work in the literature that has used strength energy function to determine the material properties for the tissue, which is the table that you see on the right. And also work in my group and with collaborators at UT Austin, we have measured the mechanical properties of porcine tissue, murine tissue, and it has the same behavior, this very nonlinear exponential behavior. And what I would like to point out here is in the bottom plots that you see, this uniaxial, off-biaxial, and biaxial response is if I take this range of parameters for human skin from the literature, and I sample, let's say I put a uniform distribution over these parameters, and I sample from these parameters, and I evaluate the stress response for these very simple cases, you'll see that the prediction in the stress becomes very much uncertain as you increase the stretch. The shading in the plots denotes the probability of the stress. So clearly, as you have more and more deformation, your prediction of the stress is more and more uncertain. And this highlights the importance to not pick a single value of the parameters if you're going to evaluate a finite element model, but to really incorporate this notion of uncertainty in these material parameters when you make any sort of prediction. Now, I would point out that here we can evaluate these analytical functions as many times as we want, but in reality, when we have a finite element model, we cannot do that. And this is where the machine learning comes into play. There is some structure to the problem that we're solving. So there should be some underlying information that we can leverage so we don't have to run a ton of finite element simulations. So what I'll show here is that you can use a combination of Gaussian process regression with dimensionality reduction to get something that is achievable that you can evaluate many, many times. So the first step would be to sample your input space. So you do have to spend a little bit of computational power in evaluating the finite element model, but ideally not as much as you would need to make any sort of uncertainty analysis. So we tested different points in the input space, and at the end we settled for these 650 points. So we have, and we do a sampling with Latin hypercube sampling, which is just a uniform, evenly distributed sampling in the input space. And we run those finite element simulations. And what you see is that the output that you get is the stress response over the entire mesh. And then the number of nodes that have a non-zero stress distribution is about 4,000. So then if you just stop right there, you would have to build a map that goes from this three-dimensional input space to this four-dimensional output space. And that's also not that convenient. But again, there is some structure that we should exploit because we are solving this PDE. So if you, for example, normalize the stress data, if you subtract the mean and divide by the variance, you can do a principal component analysis. And the eigenvalues essentially have the information, describe the variance that can be explained by these different eigenvectors. And then what we see is that actually for this case, only 3 eigenvectors describe 99% of the variance. So we don't need to use all the 4,000 dimensions of the initial mesh, but we can project this to this 3-dimensional output space. So now the problem has become from learning this or running many times the finite element simulation to only running it 650 times. And then instead of building a map from 3 to 4,000, you can build a map from 3 to 3. So that's a lot more doable. And you can do this with Gaussian processes. And Gaussian processes are basically distribution over functions, and it works in a Bayesian framework. So first of all, you set up a prior over the types of observations that you can get. So the characteristic of the Gaussian process is that any sampling of the Gaussian process at any input is going to follow a normal distribution. So the joint prior, it's going to be some normal distribution. If you have no information, you can assume a 0 mean. And then the variance is defined by this kernel function, which I'm not going to go into the details of how you pick the kernel function, but it basically describes your beliefs about the regularity of the function. And then you have some data that you have observed by doing these simulations. And then in a Bayesian framework, you can pose a likelihood based on this data. That is, what is the probability that I observe this data given this input? You multiply that by the prior, and you get your posterior. And in this case, because it's both are Gaussian, so the likelihood, you can assume a Gaussian likelihood, and your prior is Gaussian, then you can analytically get a posterior, which is also a Gaussian, and that has a predictive mean and a predictive variance. And I would like to point out here that the fact that you get not only a predictive mean, but a variance, that means that you're not just making predictions, but you are also saying how confident you are in those predictions. And that's a difference, for example, from the usual neural networks, where you would not get this variance. There's work in Bayesian neural networks. We are doing work on that as well, but the Gaussian processes have that built in, so that's very convenient. This is just the validation set. So, after we've trained the Gaussian process, we can evaluate it on a validation set and compare it against the finite element simulation. And then the one thing that you'll see here is that we are doing the comparison in the stress space. And this is because even though our map, so the Gaussian process works in this 3 input to 3 output, at the end of the day, we can project back to the stress space and compare in terms of the stress output. And the distribution of the error is something that we were comfortable with. You can reduce the error, as you can see here. There is some error, but you can reduce it by sampling more the input space. You can do this either by just sampling everywhere or do some active learning, for example. And you can also decrease the error by having more principal components if you can afford it. So once you have this surrogate, you can start to ask these other questions that you couldn't ask before. And so, for example, some of the questions that you might be interested in are, what is the probability that you're going to exceed some threshold stress? Or what is the most sensitive parameter? Or if you have to make a measurement, what would be the best measurement that you can make such that you reduce the uncertainty in your prediction? So those are things that you can do now because you have this 3 to 3 surrogate that you can easily evaluate. And so one of the things that we do is, based on these values that are available from the literature, we start with this very, very broad range of parameters. But in reality, we actually have some more information about the properties that you might assign to this 7-year-old kid. So what happens if you just pick a single set of parameters? And then you can see that the Gaussian process still has some variance because it will still tell you that it cannot do a deterministic prediction. It will have some uncertainty, even if you only choose a single set of parameters. But more importantly, what if you don't pick a single set of parameters, but rather you pick a range based on what you think is reasonable, based on your prior assumption over the parameters for this patient demographic. And then we put either a normal distribution or a uniform distribution, and then we ask for what are the probability of getting high stress values at a given region. And with that, what we find is that there's these 2 regions that are highly likely to have higher stresses, the T-junction and the temporal scar. And then if you look at the 30-day follow-ups, we did have some complication over the course of the first month in the T-junction. not in the temporal scar. So this is not a full validation that we can predict where the complications are, but it definitely points out to the fact that indeed stress is correlated with more likelihood of having complications. So that's something that we can answer now with this type of surrogate. So that's one example on the patient-specific case, and we wanted to take a step back and go back to the more idealized settings and how can we improve just general guidelines of reconstructive surgery. And these are three flaps that are commonly used. This is the advancement flap. This is called the rotation flap. And this is called the transposition flap. And I would point out that these are designed basically through trial and error. So they produce completely different stress responses, and there's flaps proposed, even recently. So we will focus on these ones. And again, we want to do some uncertainty analysis and optimization. So we follow a similar pipeline to before. In this case, we added an isotropy, so now our input space, instead of being 3-dimensional, is 5-dimensional because of these additional anisotropy parameters. And because of that, we actually have to sample a little bit more in order to get a decent error. So we had to train with 2,000 samples instead of 600. And this is something that you can get as you increase the number of samples. You can quantify your error and increase as needed. And also the PC, the principal component analysis, we need about between 26 and 30. So 26 is for the advancement flap. But we need more principal components. This shows how the cumulative explained variance increases with principal components. And in this case, you can see that it increases a lot more slowly. Once you have trained the surrogate, again, these are trained in this reduced dimension space. Then you can do the validation. Again, you have a validation set. You do a prediction with the GP metamodel. You pass it through inverse PCA. In parallel, you run your finite element simulation. And these are, for example, the median error results. In all cases, the median error is below 10%. And it looks pretty decent. And as I say, it's below 10% in all cases. So we were happy with this. And again, once you have the surrogate, you can ask these interesting questions about what the effect is of these different parameters. One of the things that you can do is a global sensitivity analysis. And doing this global sensitivity analysis at these points that we consider to be critical, we find that the direction of anisotropy is the most important factor. And it's not entirely surprising, but it's actually very useful because even though the surgeon has no control over the other parameters, it cannot control any of the other material properties, they can control the orientation of the flap with respect to the direction of anisotropy. So we can do some optimization. And in collaboration with our surgeons and also looking at the literature, we look for different cost functions that will be reasonable or that the surgeons use nowadays. And one of the cost functions is the mean strain, then a sum of wound strains, so strains near the wound, and some of the distal strains. So in the flap, only in the flap, the distal ends of the flap. And we pose two types of optimization problems, either a risk-neutral optimization or a risk-adverse optimization. And in the case of the risk-neutral optimization, we want to minimize the expected cost. And in the case of the risk-adverse optimization, we want to minimize the worst-case scenario. And the reason why we have this expectation or we have this worst-case scenario is because we can control the orientation, but all the other parameters should be drawn from some probability distribution because we don't know them for sure. And for that, you just need to evaluate a lot the surrogate. And then in terms of the actual optimization, we use either grid search or particle swarm optimization. And as you can see, grid search or particle swarm basically relies on just the ability to sample the function as many times as you need. These are the results. This is a lot of information. So let me focus on the advancement flap. And then the different rows are the different cost functions that we use, the mean strain, the sum of the wound strains, or the sum of the distal strains. And then let's focus just on one of them. And you see this shaded area. And this shaded area is because, as I said, for any particular orientation, you don't have a single value of the cost, but you have a distribution of the cost because all the other parameters are uncertain. And this is the type of histogram that you would get. If you slice this plot at different angles, you would get different distribution for the cost because you are drawing samples from these probability distributions for the other parameters. The solid line on the left column, that's the expected cost or the mean of the cost. And the red points are the worst case scenario, which we found with the particles from optimizer. And then if you minimize either of them, actually they lead to the same result. So in this case, there is not that much difference between the risk neutral or the risk adverse optimization. There is difference though between the different cost functions that you use. I would say that typically what is advocated for in the clinical setting is to have the flap oriented 90 degrees. So the first two rows are actually what you will see recommended in the clinic. And these are the results for the other flaps. I'm not gonna go over the detail of the different trends that you see, but I would say the main characteristic is that we do get a consistent minimum, even as the other parameters are uncertain. And we do get an alignment between the risk adverse or the risk neutral optimization, but we do see some difference with respect to the cost function, which suggests that there's a little bit more research needed to identify which cost function is actually the one that you should use to do any sort of optimization. We have also started doing adding some other parameters, some simple geometric parameters like changing the angle of the flap, changing the back cut length, changing the defect size. I'm not gonna cover that, just showing you that we have been exploring this, not just material properties, but also flap design. And again, I just want to point out that we are going back to the clinical case, collecting the 3D geometries, setting up the procedure, doing the simulation in collaboration with the surgeons, following up on the patients, and then eventually the goal would be, at this point we are not changing the way the plan is done. But the goal would be that as we collect more data, we do more of these simulations, that we actually can tell the surgeons what we think is the best way to go for a particular case. One of the things that we need to improve, as I said, we can get really, really good geometries, but in terms of the material properties, we're still a little bit not great. So one of the things that we have is we have bought this commercial system called the Cutometer, which allows you to get non-invasive measurements of the skin mechanical properties. And essentially the way this works is you apply some negative pressure through an orifice, you measure the deflection of the skin. So this gives you very coarse information, but it's some information nonetheless. And it's widely used in the clinical setting and for research. However, the way the inverse problem is done nowadays, and you can see this from the right, and these are two very recent publications, is that either you use an analytical approximation, which is not very accurate, or you want to use a classical inverse finite element approach. And the problem with that approach, I'll point out in the next slide, which is that if you use the classical inverse finite element approach, you ignore existing information. So in reality, you start from scratch. You want to find, the best possible parameters that give you your measurement. But it's not in a Bayesian way. In reality, you actually have some information. If you have collected data before, you should use that information. So that's one of the things that we want to do and change with respect to what is usually done. You want to have a well-posed problem. So the classical inverse problem tries to minimize cost function, for example, mean square error, and it's not necessarily a well-posed problem. What if the problem doesn't have a unique solution? So if you pose it in a Bayesian way, then you can get around that, and I'll point that out specifically in an example that I have. And the other one thing that you want to do is you want to incorporate uncertainty. So we want to do the inverse problem, but with these characteristics. So again, we have a model that we think represents the actual experiment. So we have, in this case, it's an axisymmetric model. And you want to do this Bayesian calibration. And let me walk you through this a little bit. You have a model. So this, either the finite element model, for example, let's call that f of x. which takes in some parameters and gives you the prediction of the experiment. And you can either use the finite element simulation or you can replace that with a surrogate, as I've shown before. And then the inverse problem is you want the parameters x, in this case, maybe some other hyperparameters, so that's why I use the variable z, when I know some measurement y. And the Bayesian way of posing this is I actually want a posterior distribution of the parameters, given the fact that I can evaluate a likelihood, which is the probability that I see the measurement given my choice of parameters, times a prior distribution over the parameters. And this is very important because if you have information from data that you have collected before, you should use that information. You shouldn't start from scratch. And you can go forward, even do more, which is, what if I'm not even sure about my model output? So you can also incorporate that uncertainty. All you need to do is to have a probability of your output of your model. And you just need to have the marginalization over that. So integrate over the different predictions that you might get if you are not truly confident on your model. So I'm gonna show you one example for this case. We only have two parameters that we are interested in. We have the shear modulus and we have a pre-strain. And then the height is the type of data that you can measure at different pressures. I'm gonna start with this one. So the example number 3, for which you have some shear modulus and the pre-strain that are given there. And these are the last 3 columns are the measurements. And what you can do is you sample the posterior. What ways do you have to sample the posterior? The standard way is Monte Carlo. So you can use Markov chain Monte Carlo or Hamiltonian Monte Carlo, and you can implement this easily with some tools. For example, PyMC3 allows you to define some user-defined likelihood function, and I'm not gonna go over the details of that, but this is the type of random walk that you would get from this type of Hamiltonian Monte Carlo. And that will give you a posterior distribution for your parameters. So here you see the posterior for the shear modulus and the posterior for the pre-strain. And you might say, oh, this looks terrible. You didn't do a good job giving me the pre-strain. And I would say, actually, this is exactly what you should get. Because if you look at the contour of the measurement as a function of the pre-strain and the shear modulus, and if you do a sensitivity analysis, you will see that the shear modulus is way more important. And actually, in the small shear modulus region is where you have the greatest variation. As you increase the shear modulus, you have less and less variation. So yes, it's right. If I get a posterior distribution of the pre-strain, it should be very flat because I really cannot tell what the difference is between one pre-strain or another. Whereas I can tell a little bit more about the shear modulus. So if you look at example number 2, you can see you would expect the same. You would expect a flat distribution for the pre-strain, and an even better distribution for the shear modulus, because as you have a smaller shear modulus, there's a little bit more of a gradient. And indeed, if you sample for this case, you get a much better prediction for the shear modulus, and you continue to get a pretty bad prediction for the pre-strain. It's not really a bad prediction; it's what you would expect based on the model. So this deals with this lack of unique solution that you expect in this case. So this is what we are doing. This is a little bit of a toy problem, I would say, in terms of 2D, but it really showcases this type of posing of the problem. What we are doing now is we're really going to the 3D case with a nonlinear setting. And some of the questions, again, that you can ask are, what are the best measurements that you can make that would reduce the uncertainty the most? What are the most sensitive parameters? What information do you expect to actually get versus information that you think that is not, that you won't be able to get? And again, using prior information whenever you have it. So that concludes this part of the talk. And then I only have 10 slides left, so for the growth part. So hopefully that will be okay. So the main takeaways from here.
You're fine, Adrian. You're doing well. You're fine.
The main thing is that deterministic models are not enough. There is uncertainty in the mechanical response of tissues, and this is exacerbated by the nonlinear mechanics. Computational mechanics plus machine learning enables different analyses that are not easily accessible without that, such as uncertainty propagation, optimization on their uncertainty, global sensitivity analysis, and well-posed inverse problems. And finally, that we are working in collaboration with surgeons to try to bridge the gap between computational modeling and actual clinical application. So we hope, as I said, at the moment, we're not altering the way the procedure is done, but that's definitely our hope. So that covers the reconstructive surgery part, and I will just spend a little bit of time on the skin growth project. So the motivation for this is that tissue expansion is the default treatment for breast reconstruction after mastectomy. Breast cancer affects 1 in 8 women over their lifetime and is the second most common cancer in women. And as I say, tissue expansion is the most used technique. However, rate of complications can be 15% or higher, and that doesn't include poor cosmetic outcomes that can negatively affect body image. And the way the process works biologically is by putting an expander underneath the skin and inflating that gradually over a period of months, you get new skin. So that's used not only for breast reconstruction, but as I showed before, for reconstructive surgery as well. We want, again, to have predictive models. A framework to describe the growth and remodeling of tissues is within a kinematic, within continuum mechanics with a kinematic approach in which you can split the deformation gradient into growth and elastic contributions, where the growth tensor describes this biological adaptation. And we have used this type of theory to model skin growth. This is work from my PhD, where we were interested in just seeing what the characteristics are from using different expanders, for example, in terms of growth and remodeling. However, now that in my group, we have been focusing a little bit more on collecting data in order to calibrate these models. So we have this animal model where we have pigs, we have tattooed grids over the pigs, we have a 3D photo system. We put in the expanders. The procedure is very similar to what you would have in humans. We follow up through the procedure. At the end of the procedure, we excise the skin and we quantify the growth. So we have the whole history of the formation and we have the growth at the end. And because we have these tattooed grids, we fit splines to that and we do isogeometric analysis to quantify the deformation and the growth. I'm not gonna go over some of the details of how we process the data, but the main type of data that we get looks like this. It's a little bit noisy, and this is just because the biological system is a little bit noisy. On the top left, you see the average deformation that you would get, and it's usually higher at the apex and less toward the periphery. We also quantify the pre-strain, and the main thing that I would like you to look at is this row right here, which is the growth. And what you can see is that growth increases over time. So in this case, we have a single inflation of 60 milliliters, and we take the skin at different time points. So either 1 hour, 1 day, 3 days, 7 days. And as you would expect, over time you have growth, and you get more growth in the apex of the expander and less growth in the periphery, which correlates with the overall deformation that you see on the left. So again, we want to do some Bayesian calibration of the growth model that we have used in the past. In this case, at least for the beginning, we ignore the spatial correlation. So we don't use finite element, but instead an ODE model, meaning we treat each point separately. So we don't take into account the overall deformation. And the process is the same. So I'm not gonna explain too much over that, but you basically want a posterior distribution. And again, I'll just remind you that what we are after is we want this growth function, and that growth function describes the growth rate as a function of deformation, and that's what we want to calibrate. So again, you can set up a random walk based on your experimental data. You can have a likelihood, and you have some prior, in this case, non-informative priors, and this is what we get for the growth rate. So we get a posterior distribution for the growth rate, and we also get a posterior distribution for the error. And then I'm not showing the error in the bottom plots, but this is the type of data that we get. So this is total deformation against growth at the different time points. And the black dots are the experimental data points, and the blue dots are the predictions, without showing the uncertainty in the measurement, which is about 15%. So once we have that, we can put it back in the finite element model, and we can see how the finite element model compares with the outcome. Again, this data is pretty noisy, but we do get an overall good agreement, at least in terms of the magnitude of growth and the pattern of growth. But what we did was the calibration, we did it in the ODE. And in reality, what we need to do is to do the calibration directly on the finite element model. And to do that, we, again, need to replace this model with a surrogate. Now, the one thing that I would like to point out is that instead of the usual surrogate that I was showing before, we want to be able to account for different types of models. So we have used an ODE model in the past, and what if we want to use experimental data? So we want a framework that can take different types of models. And this is usually a multi-fidelity scheme. So for this particular case, I only changed the coarseness of the mesh, but other possibilities are available. And again, you have to sample pairs of input outputs in order to build this surrogate. And in principle, it looks very similar to the Gaussian process that I was showing before. But the main difference is that now you have 3 different types of models, or however many you have. So now your kernel function actually has to do the coupling of the data at a given fidelity to the data from the previous fidelity. So you start for the lowest level of fidelity, your simplest model, like the ODE, for example. You start with the standard Gaussian process. But for the next level of fidelity, you have to basically include the posterior of that first model into as a covariance in the second model, and so on. And again, once you have the surrogate trained with these different types of data, you can do uncertainty analysis. For example, again, if we took data from this paper where they measured the mechanical properties of 300 men and women. We find a shear modulus from those data, and we can propagate that through the surrogate and show, for example, that younger adults would have greater growth with respect to older adults, but also more variance. We can do a sensitivity analysis, and that shows that the growth rate is the most critical parameter, and we can also propagate that through the surrogate. And then in this case, the growth rate data actually is the one that we calibrated from the previous, from the porcine data. And then I'm gonna conclude, this is pretty much my last slide, that growth and remodeling involves uncertainty, not only in the mechanical behavior, but also in the biological response of the tissue. And this needs to be incorporated in order to make predictions. Second, that we use isogeometric analysis and finite element models of skin growth in tissue expansion to characterize this animal model. That we use Bayesian calibration for the growth functions, and that we have a multi-fidelity Gaussian process scheme that enables data fusion from different models and can be extended to include experimental data. And this is ideal for the calibration problem under uncertainty and the prediction under uncertainty. And with that concludes the part of the talk that talks about skin growth. I would just like to acknowledge funding sources and the people that work on these applications. The people in my lab are all listed there. My collaborators at Northwestern and Lurie Children's Hospital. And then my collaborators at Purdue, Ilias Bilionis. And then again, this is sort of the overview. If you are interested in checking out some of the other projects that we work on, not just this skin growth and reconstructive surgery, please check out our website or our Bitbucket page. We have all our code associated with each publication also available, or you can email me. And yeah, I think that's all I have. So I'm happy to take.
Thank you, Adrian, for an excellent talk. So at this time, we'd like to open it up for questions. So if you have a question, you can raise your hand virtually, or alternatively, you can send me your question privately into the chat, and I can unmute you. So maybe I'll get things started while folks are deciding whether or not how to formulate their question. Adrian, one of the things I think that's interesting about this work is this. I sort of wanted to ask you, because it seems that there's a notion of path dependence in the way that the surgeries are actually conducted and the way that the skin is stretched. And so that would give rise to different options to the surgeon that might, act to minimize. And so I didn't quite understand why that's there in the model. And so I was wondering if you could explain how that path dependence is there in the actual simulations itself as well.
So we don't really look at we don't want to I guess, replicate the exact process the way the surgery is done, but really just the final outcome. So I don't know how much of a path dependence there would be
Okay.
at the end of the, I guess we do have the information in collaboration with the surgeons about basically which edge goes to which edge, and more or less which points go to which points. And that is somewhat independent of the path, I would say. So that would be decided ahead of time. So they would do some markings on the edge to know which point should go to which point. So I don't know. I'm not sure how much of a path dependence there would be. There's definitely something we haven't looked into. We basically just look at the initial point and the final point based on just these sort of point correspondences that the surgeon suggests.
Okay. Great, thanks, Adrian. Other questions from the audience?
I saw someone raise their hand before, but I missed it.
So I guess what we're waiting to see on other questions there, Adrian. So it seems to me that the starting point in a lot of simulations is actually a configuration where an existing part of the skin has been removed, right?
Yes.
And so is there a sense that you know, there's really not any choices in terms of how the skin that's actually going to be removed, and so that part of the process is perhaps not so important for you to understand or for the surgeons to understand?
Correct. Yeah, that is given by the defect that you have to remove. So yeah, we don't control that, and the surgeon doesn't control that really.
Okay, so I think we have Jessica Zhang would like to ask a question. So Jessica, I'm going to unmute you and let you go ahead and ask that to Adrian directly.
Okay, very nice talk, Adrian. So very interesting project. So I want to ask in your project, so how much influence you think in the general science, the mechanics or the physics information influence your result?
I think it's very important to understand both the, I guess, especially for the second problem, I would say there's not just variation from the mechanics, but there's this strong coupling between the mechanical deformation and the growth. So in that sense, I think it's very important to understand both at a fundamental level how much the deformation triggers the growth, but also understanding more or less what the uncertainty is on that. And that's something that we achieved with the last calibration that I was showing. That clearly shows that if you try to explain the data, you actually see that the growth is correlated with the deformation. And that is explained even with the variance that we see, the large variance in the data. The model that fits the best with higher probability is basically correlation of deformation with growth rate. So that's, I would say, a fundamental insight that we get from this type of analysis.
Thank you.
Professor Reteshian also had a question, Adrian, there. He sent it to everyone. So it reads, based on your 3 skin flap simulations, can you recommend one particular procedure which produces the least amount of stress?
Yes, that also depends on the way these flaps are designed. I would say there's different things that the surgeon will think about. So one of the things with the advancement flap, for example, produces higher stress, but it's easier to do, so you have less constraints. Whereas for the rotation flap, it produces less stress in the part where you had the defect, but more stress in the part where you didn't have the defect. So again, that will be, I don't know if the best answer is to just give the lowest stress, or if a combination of different things that the surgeon wants to take into account. Because, for example, as I said, one of the reasons why the rotation flap will be used is because maybe there's less stress at one end of the flap where you had the defect, even though there might be more stress at another end of the flap. So yeah, I don't know how to respond to that. I think the best way of doing that would be to actually collect data on the amount of complications and also what the surgeons rate as successful outcome versus unsuccessful outcome.
Maybe if one of the staff can unmute Gerard Ateshian. I don't know if Gerard has a follow-up there or not.
Thanks, John. No, I don't have a follow-up. Thank you, Adrian. That was a very, very nice talk. Very impressive. Nice job.
Thank you.
So next we have a question from Manuel Rausch. And so let's see, can we unmute Manuel? Manuel, if you're still there, why don't you go ahead?
Yeah, absolutely. Can you hear me?
Yeah,
we can.
Okay, great. I typed out the question, but essentially I'm wondering, a lot of your work still depends on this sort of classic hyperelastic constitutive modeling. And you've done all this work using machine learning, Gaussian processes to essentially get more insight in your data, but you still depend on this old classic approach in a sense. And do you have any thoughts how to move away from that and kind of get away from this constraint that poses?
Yeah, for sure. Yeah, that's not something that we have looked into, but I think you can still use some of these tools with different types of constitutive behavior that are time dependent. I mean, the growth one is an example where you have changes over time, and the surrogates that we use are still pretty good at capturing this transient, the dynamic behavior. So yeah, I wouldn't say we have to be constrained to use hyperelastic models. We just haven't done it with other sort of more realistic models, but we shouldn't be constrained. This is just being a choice, I would say, for now. But I think the growth process shows that even where you have something that changes over time, like growth, you can still capture and distill some of the dynamics with these machine learning methods. So I don't think it's a hard constraint. It's more like a choice that we have done up to now, but definitely could be changed.
I guess my question was also posed a little more general in the sense that you're constrained to a constitutive model, right? So be it a hyperelastic one or another form of constitutive model. I guess my question was more, can you move away from a priori assumptions about the form of your behavior?
Yep. So that's something that we are working on as well. We haven't published anything on that yet, but definitely we are thinking about how to not assume a parametric form of the constitutive behavior and just use the data as it is. And there's some questions there that are interesting because one of the nice things about using these constitutive behaviors that have been proposed is that they satisfy some physical constraints that you would expect for strain energy functions, like polyconvexity, for example. And that you wouldn't get if you just use blindly any sort of like machine learning tool. So we are working in sort of how do you use, for example, Bayesian neural networks, but encode some of these constraints that you need to encode so that you don't get a strain energy prediction that is not polyconvex, for example. So you can do it, but you have to be a little bit careful with that. And we are working on doing that.
Thanks, Manuel. Thanks, Adrian. So Tarek had a question, Tarek Zodi. Tarek asks, are there plans to include growth models to include minimization of scarring?
Yes, for sure. So I didn't talk about the first part of the applications that we have on wound healing and pressure ulcers and scarring, but definitely. So we want to not just do the mechanics for that problem as well, but also try to predict what the dynamics of the scarring will be after the surgery. So we definitely want to do that. We're not there yet. So we have been working a lot on Bayesian calibration of wound healing model that we have proposed based on animal data, so murine data. And the goal would be to extend that to also try to predict the scarring in the human case. So we are working on that. Thank you.
I'm sorry, Lucy Zhang also had a question there. I don't know if you can see that, Adrian, on your side. asking about including transient effects.
Yes. Yeah, great question. I think same idea. Right now we have, I guess we know that the stress will be correlated with the wound healing outcomes. And I would say as a first simplification would be to just look at the stress, because we know that it's going to be connected to the wound healing outcomes. But definitely the goal would be to not just predict the overall stress response, but how does that affect the scarring. And yes, we are interested in doing that. And yeah, we are working on that. So yeah, that's a good question.
Thank you.
Okay, great. And we do have somebody who raised their hand. There's a Marcelino Chavez. Can one of the staff unmute Marcelino so that he can ask a question?
Okay.
Go ahead.
Yes. Hi. Hi, Adrian. Thank you a lot for the talk. It was very interesting, and it's a lot of work. My question is, I guess it's just a minor point, and I guess it was sort of answering one of your previous answers. Just when you're talking about treating the forward model as a random variable, so you're talking about the uncertainty on your forward model that's coming from the uncertainty in the parameters of the model, right? Not in the functional form of the mechanistic model. Is that correct? Or at least in this work?
Not just the parameters of the model, but actually, for example, if you have a Gaussian process, which is what we have so even if we assume that the finite element model is a perfect representation of the experiment, mm-hmm. because we don't evaluate the finite element model everywhere, we just replace it with a surrogate, then in that case, for example, the surrogate has some uncertainty. So even for a single set of input, even if you think that your input is deterministic, your output can still have some variance. And the best example would be even if you trust your finite element model, but you replace it with some surrogate, then you have a prediction that is not a single value, but is some distribution.
Okay, thank you. And just a second minor point too is, in some points you use traditional, I think, standard finite elements and also isogeometric analysis. Is there a reason why you use one or the other in different situations, or I don't know if you could talk about your choice, whether using one versus the other for skin modeling?
That's a good question. Yeah, I think isogeometric is very powerful for shells, and that's how I got interested in it in the first place. And it just happened to be a really good model for this, to match the porcine experiments, because in the porcine experiments we have this tattooed grid, so we have this sort of parameter domain that it remains constant. So it's sort of like the mesh is fixed for the porcine model. It just seemed more natural for that particular case. But in general, I really like it for modeling skin, because it's a thin material. I don't know. I would say, yeah, we have some code in Abacus using just standard finite elements. I like the isogeometric for shells. And at the end of the day, sometimes it's just the availability of some of the functions that we have implemented in Abacus. Sometimes it's just more convenient to use. But I would say either one, I would use.
Okay. Thank you. That's all my questions. Thank you very much. And great talk.
So Adrian, Chaim Wiseman also wanted to know how important you thought that anisotropy in the skin model itself could be.
Really, really, really important. So for the flap designs, basically is the most important parameter, more than any other material property that you have, because it has these really long range effects. If you change the anisotropy, you can get stress distributions that change in a very large area. So it's very, very important. And even, I didn't show this, but for the inverse problem of the cutometer in the 3D case, you can actually design the opening. This is what we have been doing. You can design the opening such that you get the most change in the output with different openings. And that's something that you can do because the anisotropy is very important. So you could design the opening of the cutometer to identify the direction of anisotropy with few measurements, as few as 3 measurements. You can identify the orientation of the fibers. So it's very, very important.
Thank you.
Okay, well, so thanks,
I
Adrian.
have
again.
one more question. Can I ask one more question?
Yeah, go ahead if it's short.
Short, yeah. The question is about when you do the sutures, right, with the flaps, do you consider re-rupture when it ruptures maybe again? Or how do you consider that rupture effect?
We haven't considered that. That's a good question. Yeah, it's something that we could incorporate. It makes the model more time consuming and more complex. So it would be a little bit more difficult to try to replace that. But that's something that it could be very important. So we should definitely look into that.
Thank you. Thank you.
Thanks, Adrian, again for an excellent talk. We appreciate it very much. So thank you all for attending today's talk. It was great to see everyone. So we will have another one next week. We have Steve Sun presenting from Columbia next week, and I think the announcement about that and registration page will be distributed sometime this afternoon. So please look for that. Otherwise, nice to see you all, and enjoy the weekend. Thanks very much.
Thank you very much.